Logic is simply the science of reasoning. It gives us the rules and structures we use to make arguments, draw conclusions, and avoid errors in our thinking. The systems of logic we're covering today are the different tools that help us reason in various contexts. Some are used in formal proofs, others for everyday problem solving, and some are even applied in fields like computer science and artificial intelligence. Let's dive into each one, starting with the classics. 1. Classical logic. Propositional and predicate logic. Classical logic is the most fundamental system of reasoning. It's divided into propositional logic and predicate logic, each focusing on different aspects of reasoning. Propositional logic focuses on propositions, simple statements that can either be true or false. The power of propositional logic comes in how it combines these simple propositions using logical connectives like and, or, and if, then. Example, imagine you say, if it's raining, I'll take my umbrella. This is a conditional proposition. The truth of the second part depends on the first. In propositional logic, we would analyze the relationship between the two propositions, it's raining and I'll take my umbrella. Predicate logic goes further by involving quantifiers and variables, which allow us to talk about objects and their properties. Instead of just stating, it's raining, we can say, John owns a car. Here, we can explore whether John owns some car or all cars. This system is powerful in formalizing reasoning and proving statements in mathematics and computer science. Example, all humans are mortal. Socrates is a human. Therefore, Socrates is mortal. In predicate logic, we break it down to understand how relationships between individuals and general categories work. Classical logic is like the foundation of logical reasoning. It's structured and clear, but it's also limited. It's about establishing validity, whether the conclusion follows logically from the premises. 2. Aristotelian logic. Aristotelian logic, also called syllogistic logic, was developed by Aristotle over 2,000 years ago. It focuses on syllogisms, which are arguments consisting of two premises and a conclusion. Example, here's a classic syllogism. Premise 1, all humans are mortal. Premise 2, Socrates is a human. Conclusion, therefore, Socrates is mortal. This form of logic was one of the first formal systems and is crucial for categorizing information. It deals with categories, humans, animals, etc., and tries to reason about their relationships. While classical logic has more general rules, Aristotelian logic is much more focused on specific categorical reasoning. Aristotelian logic isn't just about deduction. It's about creating categories and understanding how things fit within them. For example, if we want to prove that all humans are mortal, we can begin by defining humans and mortal within the context of the syllogism. 3. First order and higher order logic. First order logic, also known as predicate logic, deals with the relationships between objects. It lets us reason about properties of objects, like Socrates is mortal, and their relationships, like Socrates is a human. Example, all humans are mortal. Socrates is a human. Therefore, Socrates is mortal. This works well for most reasoning tasks in everyday life. Higher order logic builds on first order logic, allowing us to reason about sets, functions, and other logical structures. It's a more powerful system that lets us discuss theories of logic themselves, or reason about abstract concepts. Example, consider saying, the property of being human applies to Socrates. Here, you're talking not just about individual humans, but the property itself, being human. Higher order logic is particularly useful in advanced mathematics and theoretical computer science, allowing for more sophisticated formal systems. 4. Modal logic. Modal logic is used when we reason about possibilities and necessities. It introduces modal operators like possibly and necessarily, which help us reason beyond what is strictly true or false. Example, it's possible that it will rain tomorrow, or it is necessary that the sun rises every day. In modal logic, we don't just deal with what is, we deal with what could be or must be true. This system is widely used in philosophy and computer science, especially in situations that require reasoning about alternative possibilities or future events. 5. Fuzzy logic. In fuzzy logic, things aren't just true or false. Instead, we can reason about degrees of truth, from completely true to partially true to completely false. Example, imagine the statement, it is hot outside. In fuzzy logic, rather than just saying yes or no, we say, it is somewhat hot, or it is very hot. This system helps in real-world decision-making, like in AI systems and automated controls, where vagueness and gradients of truth are important. 6. Intuitionistic logic. Intuitionistic logic challenges the idea that truth is just something you can declare. It suggests that truth only exists when you can construct a proof of it. Example: suppose someone says, "There is a chair in the room." In intuitionistic logic, the statement doesn't count as true unless you can prove that chair exists by constructing a proof of its presence. This system is key to computer science, particularly in areas where we build formal proofs for programs and algorithms. 7. Non-monotonic logic. In non-monotonic logic, adding new information can change your conclusions. This system reflects real-world reasoning, where facts evolve and we adjust our conclusions accordingly. Example: if you initially believe your friend is at work, but later learn they're on vacation, your earlier conclusion changes. Non-monotonic logic allows us to revise our conclusions based on new information. 8. Relevance logic. Relevance logic insists that arguments should not only be valid, but also relevant to the conclusion. The premises must directly support the conclusion in a meaningful way. Example: all dogs have 4 legs. Fido is a dog. Therefore, Fido has 4 legs. This is valid, but saying, John is tall, therefore, Fido has 4 legs is irrelevant and invalid. 9. Paraconsistent logic. Paraconsistent logic allows contradictions without collapsing the entire system of reasoning. In classical logic, contradictions lead to an explosion of conclusions. But in paraconsistent logic, contradictions can exist without invalidating the argument. Example: Fido is both alive and dead. This might seem like a contradiction, but paraconsistent logic allows us to explore situations where contradictions can coexist in specific contexts, like in quantum mechanics. 10. Informal logic. Informal logic deals with reasoning and arguments in everyday life. Unlike formal systems, it focuses on persuasion and practical reasoning used in debates and conversations. Example: I think the new Marvel movie will be great because the last few were amazing. This is an informal argument based on personal experience and expectations, not a strict logical proof, but still reasoning. 11. Constructivist logic. Constructivist logic focuses on the idea that knowledge and truth must be constructed through evidence and reasoning. Example: when solving a math problem, you don't just accept the answer, you need to construct a solution step by step. Only when the solution is constructed is it true. 12. Temporal logic. Temporal logic helps us reason about time-dependent events, such as when things will happen or must happen. Example: in programming, you might want to say, task A must happen before task B. This system allows you to reason about the order of events over time. 13. Description logic. Description logic is about describing relationships between concepts in a formal language, often used in semantic web and ontology-based systems. Example: in a database, you might have categories like animals, mammals, and dogs. Description logic helps define the relationships between these categories, making information easier to search and analyze. 14. Quantum logic. Quantum logic helps us reason about the strange behavior of particles in the quantum world, where classical logic doesn't always apply. Example: imagine a particle that can be in 2 states at once. Classical logic would say this is impossible, but quantum logic allows us to reason in a way that accounts for this paradox. 15. Default logic. Default logic allows us to reason with assumptions or defaults that are generally true unless proven otherwise. Example: when you go outside and it's cloudy, you might assume it's going to rain unless the sun comes out. This reasoning allows us to fill in gaps in knowledge when we don't have all the facts. As we've seen, there are many systems of logic, each tailored to specific types of reasoning and different areas of life. Whether you're solving math problems, making everyday decisions, or even exploring the depths of quantum physics, understanding the various systems of logic gives you the tools to think more clearly and reason more effectively. Which of these logic systems interests you the most? Let me know in the comments. And don't forget to like, subscribe, and hit the notification bell for more thought-provoking discussions on the foundations of reasoning.